Alrighty, excuse me. So this is Recreational C Programming. And yes, I'm kind of stealing my presentation style from SICP. Good course. All right, here's what you really are here for, though, is the most popular algorithm to compute in the world, so far as I know. It's called Secure Hash Algorithm 256-bit. Now, it's the proof of work algorithm used by Bitcoin, but don't worry, I'm not going to try and sell you any Bitcoin. The current hash rate of the network is estimated to be about 600 exahashes per second. To give you an idea of how big of a number that is, let's look at a million. Not bad. If we go to, that would be megahashes, gigahashes, that would be 1,000 times that, terahashes, it's 1,000 times that. There's a petahashes, 1,000 times, so, you know, we're getting to 1,000 million millions. And then you've got, what is it? Yeah, mega, giga, tera, peta, exa. And of course, what the network is doing is not 1 exahash per second. It's doing 600 of them, roughly. So there's all your zeros. That's some serious computing power. So, what I really want to do is, I'll use the whiteboard for a high-level overview of what the SHA-256 algorithm does, and then I'll show you the code for the deep dive. So there's a thing you got called a message. And that's going to produce a 256-bit hash value, also known as a message digest. These are used extensively on the internet to confirm that a file has not been messed with. So how big is 256 bits? Unfortunately, I can't do math in my head very well, but But if you do the log base 2, 256, that'll give you some big number. And let's just say that if you want to brute force guess hashes, it'll take you a while. In fact, the big property of the hashing algorithm is that it's what's known as pre-image resistant, meaning, so you got message A, and message B, it also gives you a 256-bit hash. These hashes will not be equal to each other, almost certainly. If you can find two messages that come to the same hash, it's estimated to be somewhere in the order of 1 to the 128 operations using a birthday attack, meaning you would have to just randomly do messages and hash them and see if they collide. I think that math is right. I actually suck at math. And in fact, I fixed a bug just this evening in my algorithm, my implementation. Now, I've written my implementation to comply with National Institute of Science and Technology, FIPS 180-4. That's where the spec is, and in my GitHub, I've got a link to it as well as an actual copy of it. So, yeah. And I used straight C++. There's no boost, there's no third-party libraries. It's strictly what you can do with the language. So, what do we do here? Step 1 is padding. What we want to do is break the message up into chunks that are 512 bits, which is 16 32-bit words. And I'll be using words a lot. It's a machine words. So yeah, a word is a 32-bit unsigned int. Not only that, operations done on the words are modulo 2 to the 32-bit. modulo 2 to the 32-bit arithmetic, meaning basically when the word overflows, it just wraps around. And there's actually a fair bit of that going on in the algorithm itself. Okay, so the message is padded, if necessary, so that it's a series of 5 12-bit blocks. And then we initialize, we have an initial hash, H0, which is 8 words, which are the square roots of the first, I'll just say P1 through, or rather P0 through P7. They're the fractional parts of the square roots of the first 8 prime numbers, 2, 3, 5, 7, 11, 13, you get the roots. So that's the initial hash value. And there's also a set of 64 constants which are derived from the cube roots of P0 through P63. My notation's not quite right, but they're the fractional parts of the cube roots in hexadecimal, by the way. You'll see that in the code. So simply what happens with each of these guys, we start with the initial hash. We're going to create a message schedule, which is (16 words from the message, and then 48 more words, which is the sum of 4 of these. It's going down, we're adding 4 of these, and 2 of them will have some sigma functions applied to. I'll go to the sigma functions in the code. So they basically scramble up the bits. So we have H0 up here, the message schedule, and our constants, you know, 64 constants. And then we go through the compression function that is running the schedule. This happens 64 times. So you got 64, 64, and there's a lot of addition going on. Basically, we're adding that to that, and there's 8 words here which are shifted to the right, And each time here we have some temporaries. T1, tell you what, let's see. Let's just leave that. We got a T1 and a T2, which are themselves, function to take these guys and just, scramble the bits up. And there's summation as well. So there's a lot of adding. And the addition is modulo 32, 2 to the 32 arithmetic. So it wraps around. So what we end up with here, after we're doing things, is we have H0 plus the intermediate that we come up with. And we do that for each block. So this basically feeds back, and and they just feed on and on and on, changing your original digest into the final message digest, which comes out the end of the algorithm. So have I covered that completely? Message padding, breaking into blocks, turning each block into a message schedule, running the schedule, and then moving on to the next block. Yeah, I think that's that. So let's see what the code looks like. And I think I'll try and throw in a little animation of a single block. I usually don't comment my code as heavily as this, but here we go. And by the way, this guy, hopefully that site is still up because it's pretty cool. So let's just go in, jump right in, shall we? Got the normal includes. So the type aliases, I already told you, word is a 32-bit unsigned integer. And the purpose of these, well, as you can see, is to match the wording that is used in the specification. And this whole program is actually designed to be more or less a translation of the specification from English into C++. And here we've got the 64 constants that I mentioned that are the cube roots of the first 64 prime numbers, and the initial hash. Now there's some auxiliary functions that I didn't go into. CH is, as you can see, it's called a choose function. It's taking 3 inputs and returning a single output. So we're going from 96 bits down to 32 bits. So that loses 64 bits of information right there. And the same deal goes on with the majority. It's doing a slightly different function, but again, it's 96 bits in, 32 bits out. Now for the sigma functions, these first two are used in the actual running of the schedule. For T1 and T2. And the second two here are used in the creation of the schedule. Now, an interesting thing about these sigma functions is they actually are a one-to-one mapping. That is, if you pass the output into the input over and over again, you will loop. And you'll actually loop fairly quickly with this one, 4-4. I believe it's 32 iterations, gets you back to where you're going. 4-5 only takes 16. However, 4-6 jumps up to nearly 50,000. And 4-7, it's over 65,000. So these take a long time to reverse if you're, interested in reversing them. And these are the only four that are even remotely reversible. So we come to our padding that I spoke of, which gets all the blocks to multiples of 512 bits. And there's a conditional. We have 4 cases here. A 0 length message, not very exciting, obviously. A message that comes out to an even 512 bits or 16 words. Those are great because we don't have to do anything with one of those. The message padding, as you'll recall from above, the padding is a byte vector. And the size, which I didn't talk about on the whiteboard, I forgot to mention that. The size is the size of the message in bits, the length. So L is the length of the message in bits, and it's in a 64-bit unsigned int, as you can see. And when padding is required, that size gets tacked on to the end. So 2 messages of the same length will get the same size tacked on to the end. And then I'll do a little bit of a casting trick here to turn basically a 64-bit integer into the byte array, stick it in to the padding and return the padding. Technically, I'm not really teaching C++. I'm just basically doing demonstrations of C++ things. But yes, padding is also a vector of the same type that the message is. So this is the schedule I talked about. It's fairly easy to create. This first line, we're just copying the 16 words to the beginning of the schedule and then filling out the remainder. And here's where you can see the sigma functions being used and 4 additions. Oh, I can use that beep for sync. Anyway, the additions basically create a schedule where, unless the first 16 elements were all zeros, it's going to very, very quickly become a scrambled up mess. So you're already getting a degree of obfuscation just in the message schedule itself. So after we've created the schedule, as you can see, the schedule function, it's taking a block as input. The block is, your 16 words, 512 bits. So we run the schedule. This is where the magic happens. We're getting an initial digest. The first time round, it's the digest you saw above. And then each time we process a block, we're adding to the digest, doing modulo arithmetic. we've got T1 and T2. I suck with the keyboard. And these get added together and become the first column. And then we're shifting. T1 gets added again to D in the middle column. So as you can see, this is basically a big right shift going on each time, with a new A being T1 and T2. But T1 and T2 are based on the previous intermediate values. This function just takes the message, which is a vector of type byte, and obviously here we're just calculating the size, initializing the digest. I normally don't comment like this, but I actually originally did this so that I would understand the function myself. And a great way to understand it is to explain it to someone else, like you perhaps. And I've got a pair of nested do loops that just read through the message a block at a time. Each block is put into a made into a schedule, and then the schedule is run. And it does that for the entire message. Bitcoin does an interesting thing. So I created this function. Bitcoin actually, as you can see, it does the SHA-256 hash, and then it does the SHA-256 hash again on the digest that came out. Now we know what the digest size is since it's a fixed size, so we don't need to worry about doing the padding. I can just initially create a digest and just hash the digest. Although I do not get exahash rate or even gigahash rate with this program. And then I have a little harness here to read in. You can't see my hands. So I read in the arguments that are passed in on the command line here. If there's no arguments, I have a little help text. Then initialize the message, set for when I'm double hashing, but then this iterates over the files that I've passed in. I can pass in a whole bunch of files, especially when using xargs. So this will hash loads of files, which is pretty cool, because the function I was testing against only hashes one file. And of course the whole thing is in a try block. So that's really the completion of the program. As you can see, it's not a big program, and it's on GitHub under fudmotten/SHA-256. So I'll put the link in the description box. But this does it all. Boom. So there you go. That's the SHA-256 hash algorithm. And hopefully you'll find the code is quite readable, because that was my intention, seriously, was to make the code basically a transliteration of the specification. So it's not optimized super, but it's not slow either. Although I haven't actually timed it against the program I was using. But I mean, I can just blow out of this and so what have we got? I've already, let me run the C++ line again because I have upgraded it. I did a bug fix during the night, so standard equals C++. Yeah, C++ 20. You do need 20 for this because of the rotation, the bit rotations. We'll optimize it. Make the output SHA-256. Whoa. Okie dokie. $40K, that's not too bad. So it can hash itself. And that's what it does. And the test function I was using is SHA-2. And you can see they agree with each other. So that's it. If you got this far, thank you so much. And please like, subscribe, you know, all the things, ring the bell, because I would kind of like to make some money doing this if possible. Sad but true.